Hello, welcome. In the last session, using Euclidean algorithm, we saw that if a and b are two positive integers and d is the GCD of a and b, then we can find integers x and y such that d equal to ax plus by. That is, GCD of two numbers can be expressed as a linear combination of those two numbers. This identity we called as the Bezouts identity. We have also seen in the last session itself that there is a very important consequence of Bezouts identity. We know that if C is a common divisor of A and B and D is the GCD of A and B, then C is less than or equal to D. That is, D is always greater than or equal to any common divisor. But Bezouts identity told us that something much more interesting is happening. Bezouts identity told us that if C is a common divisor of A and B, then not just that C is less than or equal to D, but C divides D. After this, now we are going to see an interesting way to derive Bezouts identity without using the Euclidean algorithm. The way is interesting because the same technique we will be using probably after some time in ring theory. Here comes the theorem that we promised, this result that we promised. GCD of two positive integers A and B is a linear combination of A and B. And this is precisely the Bezouts identity because we have seen that if D is the GCD of A and B, then there exists integers x and y such that D is equal to ax plus by. But we are going to derive this theorem using a different technique. Okay. So what we need to show is that the GCD of A and B is a positive integer of the form am plus bn for some m and n. So this is what we want to show. We want to show that GCD of A and B is a positive integer of the form A alpha plus B beta, where alpha beta are some integers. This is what we want to precisely show, that GCD of A and B is a positive integer of the form A alpha plus B beta, or it's a linear combination of A and B. So to show that this is a positive, this is a linear combination of the form A alpha plus B beta, we will consider all such possible linear combinations. Consider all such linear combinations of the form AM plus BN. Consider all possible linear combinations of A and B. And we call that set of all such linear combinations to be equal to S. So S is of the form, elements of the form AM plus BN, where M and N are integers. We have to show that GCD is an element of the form A alpha plus B beta. But remember that GCD is, we know that GCD is a positive integer according to our definition. So this S consists of probably positive as well as negative integers. Question number 1. Is there any positive integer in S? So this is the first question we are asking. Does S contain a positive integer? See, m and n can be any integers A is already given to be positive, B is also positive. But if you look at this M and N, by suitably varying this M and N, we may get A inside this S. But what is that possible choice of M so that we will get A inside S? So put M equal to 1, N equal to 0, then we get A belongs to S, and A is of course positive. Similarly, if we put M equal to 0, N equal to 1, we will get B belongs to S. So A and B belongs to S, therefore S definitely contains, these together imply that S contain positive integers. See that we have to find GCD in the form A alpha plus B beta, but GCD is positive, so we have to look for elements of the form AM plus BN, and we have to locate D among these AM plus BN. So the first step is to verify that AM plus BN, by considering all elements of the form AM plus BN, we will definitely get some positive integer. That's guaranteed, because AM plus BN consists of A, AM plus BN consists of B, therefore S definitely contains positive integers. Now, we want D to be a positive integer. D is a positive integer. Therefore, we are not basically interested in the negative elements, and negative elements or 0. S definitely contains 0 because M equal to 0, N equal to 0 will give 0 inside S. But we are not interested in negative or 0 in S. We are only interested in positive elements because we want the GCD to be a positive integer. So the element starting from 0 downwards in S is not at all interesting for us. So we will consider a new set. S dash equal to, this is equal to AM plus BN, where, or in other words, we will write like this: S dash equal to some element, what should be called, K in S, where K greater than 0. Therefore, this is of the form K is in S, therefore it is AM plus BN with M, N in Z, but the extra condition that AM plus BN is positive. This S prime is non-empty, Why non-empty? Because A belongs to S prime and B belongs to S prime. So this is the first step we have. Okay. Now if D is, suppose that D prime is the GCD. Suppose we use the symbol D prime for the GCD of AB. We need to show that D prime is an element of the form AM plus BN, AM plus BN positive. That is, we need to show that D prime is in S. But just observe one thing: if D prime is GCD of A and B, then D prime divides A and D prime divides B. So this is very clear. So D prime divides A and D prime divides B. D prime is already greater than 0. Divides A, divides B. So it divides AM plus BN also. So this implies that D prime divides AM plus BN also. But we want D prime to be an element in S prime. We want GCD to be a linear combination of the form AM plus BN. Therefore, we want D prime to be in S prime. So if D prime has to be in S prime, since D prime divides every element in S prime, the possibility is that D prime is going to be the least element in S prime, because if D prime is not the least, suppose that there exists some other integer in S prime which is less than D prime, then D prime cannot divide it. Therefore, most probably, or if at all, if D prime has to be in S prime, then D prime must be the least element in S prime. So we need to look for the least element in S prime and probably try to verify that the least element in S prime is actually the GCD of A and B. So our next aim is to try to verify that the least element in S prime is the GCD of A and B. But even before going to do that, we need to verify that S prime definitely contains the least element. But what is the guarantee that S prime contains the least element? Because not all sets contain least elements. Example, suppose that we are considering the set 1, 1 by 2, 1 by 3, etc. going on like that. There is no least. There is no least in this set, because this is becoming smaller and smaller and it is going towards 0, but 0 is not there in that set, therefore there is no least in the set. So we cannot assure that S prime will also be having a least element. What we are saying is, if the GCD has to be there in S prime, it must be the least element, because GCD always divides every element in S prime. So if GCD has to be there in S prime, it must be the least. But what is the guarantee that least element exists in S prime? One very important observation that we have made previously, that important observation is known as the well-ordering principle. What is well-ordering principle? Well-ordering principle says that, so well-ordering principle states that every non-empty subset of the set of all whole integers W has a least element. We are going to make use of this property. S prime is a set of all positive integers of the form an plus bn, therefore it's a subset of W. S prime, we have already seen that it contains A, it contains B, therefore this is non-empty, therefore S prime has a least element. So we located a least element in that, call this least as D. Our aim is to verify or to see that D is the GCD of A and B. This is what we want. Okay. So to show that D is the GCD of A and B, we need to verify that D divides A and D divides B. How do we verify that? Since we know that A belongs to S prime, B also belongs to S prime, D is definitely, D divides A and D divides B, and A belongs to S prime and B belongs to S prime, and D we have chosen to be the least in S prime, so D is going to be less than or equal to A, D is going to be less than or equal to B for sure. But how will you show, how can we show that D divides A and D divides B? We are going to make use of division theorem. By division theorem, there exist integers Q and R unique such that A equal to DQ plus R with 0 less than or equal to R less than D. This is known. Now, some rearrangement. What is R now? R is equal to A minus DQ. But what is D? Now D belongs to S prime. D is least in S prime. Therefore, there exists alpha, beta in Z, because D is in S prime, such that D equal to A alpha plus B beta, and this is greater than 0. So we will substitute for D here. So we will get A equal to R equal to A minus A alpha plus B beta, and therefore we have A, okay, one Q is also here, A into 1 minus alpha Q plus B into beta Q. But this is a linear combination. This is greater than or equal to 0. So this is the linear combination of the form AM plus BM. So this is some M, this is an integer M, this is some integer N. one more thing, one more important thing. R is less than D. If R is greater than 0, what will happen? R is greater than 0, it means that an element less than D that's greater than 0 and is of the form An plus Bn, then R equal to Am plus Bn greater than 0 belongs to S prime, but D is least in S prime. Therefore, this is not possible. So R cannot be greater than 0. But R is greater than or equal to 0 and is less than D. So what is the only possibility left? So R must be equal to 0. Therefore, A equal to DQ or D divides A. Similarly, D divides B also. So the very first thing that we want to verify is D divides A and D divides B. That is now done. What is next? So next thing we want to verify that if C is a common divisor, if C positive and C divides A and C divides B, then we have to show that then C is less than or equal to D. This is the next thing that we have to verify. Okay, C divides A and C divides B. C divides A and C divides B. So that definitely implies that C divides Am plus Bn for any M and N. Therefore, in particular, this implies that C divides D. So C is positive, D is positive, therefore C must be less than or equal to D. Therefore, both these conditions are verified. What are the two conditions? D is a divisor of A, divisor of B, so D is a common divisor. Any other common divisor of A and B is less than or equal to D. Therefore, D equal to GCD of A and B. But what is D? Where is D? D belongs to S prime, and S prime is equal to set of all Am plus Bn, where M n integer and Am plus Bn greater than 0. Therefore, D must be of the form A alpha plus B beta for some alpha beta in Z. So we have derived the business identity in a different way, and we verified that GCD of two positive integers A and B is a linear combination of the two integers. We are going to see an immediate consequence of what we just proved. We are going to see that the set of all integers of the form Am plus Bn, it is nothing but the set of all multiples of D, where D is the GCD of A and B, where D equal to GCD of A and B. This can be seen easily. So we know that we have seen that D is the least positive integer in S. Okay, we saw that D is the least positive integer in S. D is least positive integer in S, that we have already observed. And not only that, D divides D is the GCD, so D divides A and D divides B. Therefore, D divides Am plus Bn implies that every element in S is a multiple of, so this is equal to S, every element in S is a multiple of D, or in other words, S, every element in S is a multiple of D means that it is in DZ, or S is a subset of DZ. Okay, this is what we have just now, this is the consequence of what we have just now seen. Now, on the other hand, if we have to show that S is equal to DZ, we have to show that S subset of DZ and DZ subset of S. Now, suppose that we choose an element from DZ. Let DQ belongs to DZ. We know that D is the least positive integer in S. D is equal to A alpha plus B beta. So DQ equal to A alpha plus B beta into Q. This is equal to A alpha Q plus B beta q, but this is of the form am plus bn, therefore this belongs to S. So every element in dz is going to be there in S. So what is the conclusion of these things? So these two things together imply that S equal to dz. So linear combinations of the form an plus bn is nothing but it is a set of all elements of the form dq, or it is equal to dz. Now we have an interesting problem using the consequence that we have just seen. So we are going to define if A, B are subsets of Z by A plus B, we are defining this to be equal to the set of all A plus B, where A belongs to A and B belongs to B. So this is sum of all elements in capital A and capital B. Question is the following. Identify the set 3z plus 4z. So according to your definition, 3z plus 4z consists of elements of the form A plus B, where A is coming from 3z, B is coming from 4z. So we have to identify this set 3z plus 4z, or say that exactly what are the elements going to be there in this set. Okay, probably we can have a look at what's happening here. So if you try to expand this is going to be somewhat tedious job. 4z, this is equal to so definitely 3 is there, definitely 4 is there, definitely 3 plus 4 is there. Now 3 into 2 plus 4 into 1 is going to be there, etc. But if we proceed like this, it's going to be a huge task for us to verify that what exactly this set is going to be. But instead of that, so what are the elements in 3z plus 4z? Okay, we will see 3z plus 4z. We will try to write down the symbolic definition for this set. This consists of elements of the form A plus B, where A is from 3z and B is from 4z. So elements from 3z will be of the form some 3m. So this is nothing but 3m plus 4n, where m belongs to z, n belongs to z. 3m is A, 4n corresponds to B. But we have just now seen that this is nothing but equal to d into z, where d is the GCD of 3 and 4. But what is the GCD of 3 and 4? This is equal to 1, because 3 and 4, we have already seen that n plus 1, if we choose a positive integer n, then n plus 1 will have GCD equal to 1. Therefore this is equal to 1z. But what is 1z? This is equal to z itself. So 3z plus 4z is nothing but it's equal to z itself. Now an exercise for you. Identify the set 5z plus or 15z plus 25z. Identify the set 15z plus 25z. This is an exercise.